Okay, let's get started. This is the last video in this playlist, and what you'll see here is the answers to the exercises. So let's go on and see what we got. So for the resistor, as you recall, we set the initial values, but the kicker here is that we set the covariance to 0. And then if you crank through the recursion a couple of times through the loops, you'll see that K never changes, and so the estimate really never changes from the initial value. Okay, and that's due to the fact that P of 0 is 0, of course, but because phi of K is 1, there'll be no change in the estimation. It's always constant. So we never get any expansion of uncertainty due to phi, because phi is 1. So you really need to have some non-zero value for the initial covariance in order to get the estimation started. Otherwise, you're going to have a gain of 0 every time. So the second problem was to change the measurement model by adding an identical voltmeter to the one identical to the first one. So to do that, you need to change the Z measurement vector to be a column vector with 2 rows. And you need to change the H and the R matrices so that you've got H looking like this, where you have the 2 rows in 1 column with a 1 in each position. Because when you multiply it times the state vector x, which is a scalar, you'll get the measurement of each voltmeter. And the model includes some measurement noise, V1, V2, which is Gaussian zero mean with variance of sigma squared. And R is also a 2x1 matrix that has identical values sigma squared in both entries because the voltmeters are identical. Now for the third one, we say let's take a voltmeter, for the second voltmeter, make it less accurate by a factor of 2K. And so now in R, you're going to have a 2 sigma squared down there. That's the only difference. The measurement model pretty much looks the same. It's just that the variances are different. The lower factor there, 2 sigma shows up in the denominator, so you're dividing by a bigger number, and so the gain is going to effectively de-weight the use of information from the new voltmeter, as it should, because it's less accurate. Then I said in problem 4 to modify your own copy of Run Average Demo and change the amount of process noise. So once you do that, you'll notice that the running average estimator will struggle to converge because it really doesn't make use of any of the process noise statistics. Kalman filter, however, has no trouble following the process noise, even though there's measurement noise involved. So we'll look at the 2 charts here. You can see the one on the right is with the Kalman estimator. You'll notice that the black line for the estimator is hugging the blue line very, very closely. Okay, the same process noise is present in both models. It's just that the model on the right is a Kalman filter. So it gives you an idea of how well Kalman filters work. So take a look at the script that I modified. I put it in the student contrib folder out on GitHub. So for constant velocity motion in problem 5, I want you to calculate the Kalman gain. Like the hint indicates, it's exactly the same as it was for the damped harmonic oscillator. It's a 2x2 problem, so the gain looks identical. Now here we've once again suppressed the minus superscripts on the right-hand side and also the time step variable j just to declutter things, but keep in mind that they need to be there. So the reason this is identical is because the structure of the P, R, and H matrices is the same as they were in the constant velocity motion or in the damped harmonic oscillator. So same structure for the gain and the same kind of measurement model. Now, the next problem, number 6, asks you to modify the measurement model and add a velocity sensor. Okay, again, we're going to have 2 measurements now, position and a velocity measurement. And so the H matrix, the Z vector, and the R matrix all have to change. And this is what we get. We use H now as the identity matrix because the first row multiplies the now two-dimensional state vector and picks out the position state and then later adds in the white noise to give you the measurement. Similarly, the second row of the H matrix is 0, 1, and so it picks out the velocity state because the second sensor is a velocity sensor. So how do the dimensions of the matrix, the gain matrix, change? Well, the number of columns of K must match the number of rows of Z. So there's going to be 2 rows of Z, so it's got to be 2. And the number of rows of K must match the number of rows in X. All right, and there are exactly 2 states, so there's 2 rows in X, so therefore it's a 2 by 2 matrix. So by how much does the RMS error accuracy of the velocity estimation change with the addition of direct velocity sensor? Now here for the answer, I will give you both for position accuracy improvement and velocity accuracy improvement. You expect both of these states to improve in their estimation accuracy. So both scripts were run with identical initial values, and the answers we got was some pretty striking improvement. 40% reduction in the error of position estimation and 60% reduction in the improvement or reduction of the velocity error estimation, as you would expect with a direct velocity sensor. So here's the TME plots. This is without the velocity sensor. So you again see that the estimation of velocity, the lower plot, is having trouble keeping up with the truth in blue. But when we take a look at the new model with the velocity sensor, you can see now we have measurements down below in the velocity estimation, and those measurements help us so the black estimation keeps up with and hugs the truth, the blue, quite well. And here's the sawtooth for position without the velocity sensor. And here's the sawtooth for position, same scale on both plots, but with the velocity sensor. So you can see dramatic improvement there. Hardly any growth from time step to time step. And here's the variance in velocity without the velocity sensor. And now here's the variance in velocity estimation with the velocity sensor. And you can see there's quite a bit of improvement here. So now let's turn to the damped harmonic oscillator. Problem number 9 says modify the measurement model. So the measurement mods are really the same as those we made to the constant velocity model. Again, we're adding a second sensor into the velocity sensor. So all those changes are the same. Of course, the phi that we used for the damped harmonic oscillator will be the same phi as it was before. There's no change there. And take a look at this modified script that I put in the student contrib folder. So how much does the RMS accuracy change for both position and velocity? Well, the surprising thing is that the position error actually increased by 18%. That was unexpected. So I'm guessing there's something I did wrong and did not use the same initial conditions. I'll have to look at it more carefully. Or perhaps I just didn't run enough samples, and so the transient errors are outweighing the steady state errors. The velocity did decrease. The velocity error did decrease as expected, so that's good. As I mentioned, the position error should have decreased. That it didn't is probably due to my problems with making sure I've got apples to apples. And possibly large transients in the averaging and the RMS averaging that's just overwhelming the total average. So if you take a look at those, run those for yourselves, put a comment in the comments below to let me know what you think the cause was and what changes need to be made in order to get an improvement, a decrease in the position error estimation. Okay, here's the TME charts. This is the both the position and the velocity without the velocity sensor, so you don't see any red lines down below similar to what we had before when we initially talked about the damped harmonic oscillator model. And then we have the TME plots with the velocity sensor. Now we've got a red line for the measurements down below, and you'll see the black estimation line is hugging the truth, the blue line, quite well. So here's the position variance, and when you compare without the velocity sensor, and when you compare it to the one with the velocity sensor, you don't see a whole lot of change there, and that's the problem. There should have been quite a bit of reduction. And when you look at the velocity estimation and its variance, its sawtooth pattern without the velocity sensor, you get this. And as you would expect, you get marked improvement in the velocity variance with the velocity sensor. So the final exercise was to add a second sawtooth plot for the velocity state estimation, which I've done in both the constant velocity motion model and also the damped harmonic oscillator motion. So just take a look at the previous slides. And of course, we saw a marked improvement in velocity variance. And the position variance, as I mentioned, is problematic. We'll have to figure out what that was. Okay, with that, we are done with this whole playlist. In this particular video, we gave you the answers to the 11 exercises that we looked at before. Reminder that the scripts are all out there on GitHub. And so what's next? Well, next, we're going to start a whole new playlist on state space concepts. We're going to drill down a lot more on modern state space theory in order to get a more solid mathematical foundation on Kalman filtering as we drill ever deeper. Okay, thank you very much, and that'll do it for this video. We'll see you in the next playlist.